Okay, so where we were last time was we were about at capillaries, right? Is that where we were? Like we did the precapillary sphincter thing, right? Yeah, I know we did that in here. That was us. Yeah? Okay. All right, so we're going to finish up the general stuff related to blood vessels, and then we'll start in specific blood vessel trace patterns. We'll do that together. You guys are still a little ahead of the other class, so you'll probably get out a couple minutes later, but don't start wiggling because then I'll just talk slower, right? You know what happens when you start getting stuff in your backpack. You're like, oh, I'm definitely giving some answers when they leave. And then just, I know you know this, but I'm going to say it. It's going to be on the recording. You have a test on Wednesday, and what does it cover? Brain, spinal cord, spinal nerves, autonomic nervous system, and heart. Okay. Not vessels, yes. Okay. But you're doing this in the lab, so this will be helpful to you. So what we were talking about is just generally about capillaries. We talked about this whole precapillary sphincter thing that allows you to shunt blood quickly back into circulation. Like this is before the tiger walked into the room, and this is tiger in the room. But now I just want to tell you, as far as talking about capillaries, this is a transmission electron microscopy showing you a longitudinal section of a capillary with erythrocytes and a platelet in it, just to show you how small capillaries are. They're hardly wider than the red blood cells that have to go through them. So they're really, really small and really, really branched all over the body. Okay, and of course we know the primary function of capillaries is gas exchange, nutrient exchange, waste exchange. So you've got capillaries just everywhere in your body. There's a few places in your body that there aren't very many capillaries, and not surprisingly, those places are not very metabolically active, meaning they don't do a whole hell of a lot. They also don't heal very well if they get damaged. And so we talked about the fact that if you looked at capillary flow, you would be higher pressure at the arterial end and lower pressure at the venous end if you looked at a capillary flow, right? So capillaries, as we mentioned last time, have basically the simplest structures of all of the vessels, because really all they are is a layer of simple squamous epithelium, which is called an endothelium, and a basement membrane, but no smooth muscle and no connective tissue in the walls. That's both good for transport, right, because it's really, really thin, and it's bad because they can't protect themselves. So, of course, if a capillary gets damaged, it breaks, and then the blood leaks out, and that's a bruise, right? But they're epithelial tissue, so they heal relatively well in a healthy person. So it's not like the bruise is going to be permanent in someone who is otherwise healthy. So I want to introduce you to the types of capillaries because they're not all the same. So there are three types of capillaries, and then there's some variations within them. So if you look at these three capillaries, what we see in here is this one is really protective, and this one is really porous. So this one will have tight junctions between the cells, and if I wanted to get something into the tissue around it, I couldn't go between the cells, I would have to go through the cells, right? And it's got tight junctions between them. So can you imagine where in the body you might find something called a continuous capillary that is pretty protective about what is transported in and out? Any idea? The aorta? Well, the aorta itself doesn't actually have capillaries connected directly to it. What is a place in the body that you have to protect the tissue from what might be in the capillary? The brain, right? Blood-brain barrier. Remember the blood-brain barrier? So it has the continuous, complete capillaries. They're the tightest of capillaries. So does that provide an impediment to oxygen and carbon dioxide transport? No, because they're lipid soluble, so they just go straight in and out, right? Anything else, kind of have to ask permission. And then we get into the next type of capillary called a fenestrated capillary. Fenestra means window. And what these are is they have fewer tight junctions, so they're not as protected. And they also have these little windows here. They look kind of like pores, but they're not all the way open. So if you took one of those simple squamous epithelial cells and stretched it out, what the fenestration would be is where it's basically just two layers of cell membrane. They're smushed together with all of the organelles and most of the intracellular fluids smushed out of the way. So that increases transport, right? Because it provides even less of an impediment to transport. You would find those, for instance, in the kidney, where I need to do a lot of filtration. You would also find them in the capillaries that are just behind the small intestine, because I need to do a lot of absorption, right? So they're better at transport, but they're not as protective. And then these big honkers right here have a couple of things going on. First of all, they have a wider lumen. What will that do to the blood flow speed? Slow it down. It'll actually slow it down. And then they have basically really big openings, no tight junctions, really, and they don't even have a complete basement membrane around them. So they're super duper porous, which is not protective at all, but it's really good for when you have to take solids in and out. So two places that you are going to find these. First off, in the liver. So all of the blood that, of course, was absorbed in the digestive tract is going to get shunted through the liver in the hepatic port system. You with me? And then it's going to go through the liver from the bottom to the top. And as it goes through, it's going to go through these wide sinusoid capillaries. That's what those are called. Okay? And as it goes through these wide sinusoid capillaries, the blood that you absorbed in your intestine was not clean. It had potential pathogens and toxins. And what if you ate poop spinach with E. coli on it, right? Are you always going to die from your poop spinach? No, you've lived through poop spinach before, and you probably will again. Because your liver, what happens here is as it's going through these sinusoid capillaries, there are these big macrophages, white blood cells, that are like sitting on top of the sinusoid capillaries and looking at what goes by. If they see any E. coli in there, they just reach down and do phagocytosis and whoop up on it, right? So in the liver, this is really about what you're taking out, although the liver actually puts stuff into it as well. But you also find sinusoid capillaries in red bone marrow. But it's not there about taking things out, it's about putting things into the bloodstream. What does the red bone marrow do? Makes blood cells, exactly. And how do you get them in? Like through the hole. That's how you get them in, right? So these are sort of the extremes. There are in between, by the way, there's like in between everything. But these are the kinds of capillaries that you actually have. Okay, and then we will move from capillaries. They unite to form venules. All a venule is, guys, is just a small vein, usually so small that you don't have to name it. It has the tunica intima, the tunica media, and the tunica externa, just like the other vessels, except for capillaries do. And then we've got the small to medium-sized veins. Those are most of the veins in your body, like the brachial vein, the femoral vein, all of those kinds of things. And then the large veins would be like the inferior vena cava. Does that make sense? So those are big honkers. So when you look at veins, let's acknowledge a couple of different things. Veins are going to be lower pressure for arteries than arteries for 4 reasons that I can think of immediately. First off, further away from the pump, yeah, lower pressure, right? Second, lost fluid as I went through a capillary bed, lower pressure, right? Third, there are about 3 to 4 times as many veins as there are arteries, which would lower the pressure, correct? And then fourth, they tend to have a larger lumen, right? So they're way the hell lower pressure. And that has some limitations because when they're lower pressure, it's hard to get blood to go through them without backflow, right? So a lot of veins, and not all of them, to prevent backflow will have valves in them, okay? And these valves are present, especially in the appendages, to prevent backflow. And the way the valve works is, let's imagine that this one was in my thigh, it's a femoral vein. What happens is this valve will open if you push on it from the bottom, but if blood tries to go backwards from the top, it works kind of like a semilunar valve, right? And it'll close it. So what will happen is the blood will go shunk, and then the next time shunk, all the way up, kind of like going up a roller coaster. So, and that's especially important in the appendages for reasons that will become obvious in just a second. So they're really far away, right? Lower pressure and all that kind of stuff. So this is called, this will work better when your skeletal muscles contract. So if your skeletal muscles contract around a vessel and it can't go backwards, it has to go forward. So when your skeletal muscles contract, like when you're exercising, you have better venous return. We call it venous return, right? The blood that's returning to your heart. Although it sounds kind of counterintuitive, what's going on with your heart has very little to do with making the blood move in your veins. Because your veins don't have a pulse pressure at all, right? So they've got the residual pressure that's left behind from what the heart really originally generated. But they're pretty low pressure to speak of, and there's not a whole lot of pressure differential. So what you have to do is you have to squish them with your skeletal muscles, and then use the valves to help move stuff back up. But there's also another thing that occurs, and that is, they call this the respiratory pump. So when you're exercising, of course, the skeletal muscle pump is going to really help with venous return. But another thing also helps with venous return, and that's called the respiratory pump. And the respiratory pump, when your diaphragm is relaxed, it's this shape, right? Okay. But when it's contracted, it pushes down, it increases pressure in the abdominopelvic, and it comparatively decreases pressure in the thoracic cavity. So every time you breathe in, you actually squirt blood up your inferior vena cava. That's called the respiratory pump. And you breathe pretty damn regularly, yes? So you don't even have any valves in your entire ventral body cavity, because you don't need them, even though the vessels are huge, right? The inferior vena cava is wide, but considering you're constantly creating this pressure differential with your diaphragm, it's just squirt, squirt, squirt every time you breathe. So that is called the respiratory pump. And that also, when you're exercising, of course, increases venous return, because you breathe more deeply and more frequently when you're exercising. Okay. Now, your veins also act as a blood reservoir, because you've got more veins than you do arteries, and it's not always in a hurry coming back through your veins to your heart. So when you are at rest, up to 65% of your blood is in your veins. But if you started running around the building, the first thing that would happen is you'd squish it back from your veins to your heart, and then send a disproportionate amount through your arteries to your capillary beds. But it's just farting around most of the time on its way back to your heart, right? Because you don't really need all 5 liters of it in any one place at that point, okay? And then, so what happens if, for instance, these valves have either a lot of pressure on the top side, or they have weak musculature and weak connective tissue around the valve? So if, for instance, there's a lot of pressure on the top, or this is really weak genetically, right? You don't have a lot of musculature, or you don't have a lot of connective tissue, then what will happen is the blood will pool over time on the top of the valve, and it will cause it to balloon out. And that is called a varicose vein. And so varicose veins look like this, okay? Yeah, and they're more likely to happen in superficial veins, because the deep veins have skeletal muscle around them, and the blood actually gets moving better in the deep veins than in the superficial veins. So you can see these varicosities when it actually balloons out. If it's in a smaller vessel, a lot of times it will actually be spider veins that you can see. Males and females both get these. Women are a little more likely to notice them, because our legs aren't as hairy. Legs are the primary place that you will actually see them. Note to self, for those of you guys who want to go into nursing, one of the most likely occupations to get varicose veins is nurse. It's because you stand too much and don't wiggle enough. So be a super wiggly nurse, or else you will probably be a fat nurse with varicose veins. It's also one of the most likely professions for obesity. But you don't have to, right? Just be one of the wiggly ones, right? Be one of the ones that gets up and goes and gets stuff, right? So that's varicose veins. Now, what happens, by the way, varicose veins also are common during pregnancy, because I've got high pressure here with all of the weight build up, and also my blood pressure is higher, and so it's harder to get the blood back. It's more likely to pool. And then, go ahead. Yeah, anything you do to reduce blood flow back increases the likelihood of varicose veins. Crossing your legs is probably nowhere near as important as not wiggling, right? But crossing your legs does impede venous blood flow back. Now, the other thing, just in case all of you who haven't been pregnant and don't want to be pregnant, I'll give you a cautionary tale. Hemorrhoids are when you have varicosities in the wall of the anal canal, which is increased in likelihood with anything that increases pressure up here because blood has a hard time. So truck drivers, hemorrhoids, pregnancy, hemorrhoids, a lot of pressure. Sometimes it doesn't go away either. So, all right, so, and we already did the respiratory pump. So any vein that is pretty large and thin-walled, it's called a sinus, and we already met some, right? We met all of the dural venous sinuses, including the superior sagittal sinus, and we met the sinus that's on the back of the heart. What's that one called? Coronary sinus, exactly. So there are several sinuses. Now, there are a few sinuses that you run into in arteries, but not very many, because arteries don't tend to like to have a very large lumen because it compromises pressure. So you're more likely to find venous sinuses than arterial sinuses, although there are a couple. Okay? All right, so now we are going to start doing circulatory routes. Okay, so we'll do the easy one first, which is just pulmonary circulatory routes. Okay, so when we look at pulmonary circulation, it's relatively lower pressure than systemic circulation. So if you looked at an average systemic arterial pressure at rest, it's like 120/80, and 120 is the pressure in your arteries immediately after ventricular contraction, which is kind of the high, right? And the 80 is immediately before the next ventricular contraction, which is the low. So 120/80, 120/80. That's what it is in systemic arteries, but in pulmonary arteries, it's usually 25/10, meaning 25 right after ventricular contraction and 10 right before the next one. So 2 questions for you. Make sure you listen to the question. So first question is, why is that adequate? Why is that pressure enough in pulmonary circulation?
You have to fill the lungs.
Yeah, it's just right there, right? It's a neighbor, right? So it's just lungs, right? So that's not problematic. And then the next question is, what is responsible for that difference in pressure anatomically? What anatomically accounts for the 120 in systemic versus the 25?
Musculature of the ventricle.
Musculature of the ventricles, right? Because the left ventricle is way more muscular, and it actually uses up about 5 times as much metabolically as the right ventricle does. So, so the general path, if I'm doing pulmonary circulation, meaning the pulmonary circuit, is from what ventricle to what atrium? Right ventricle to left atrium. Good, you know that. Okay, so, and if I am doing pulmonary circulation, I'm going to leave the right ventricle through what valve?
Pulmonary semilunar.
Pulmonary semilunar valve into what artery is this? Pulmonary trunk. And then it's going to split into the left and right pulmonary arteries. And we are, of course, delivering low oxygen blood to the lungs, okay? Although you can't see this here, and I won't make you label them, I do want to tell you that the pulmonary arteries generally split into 3 right lobar arteries because you've got 3 right lobes, yes? And 2 left lobar arteries because you've got 2 left lobes. They never draw them on any pictures. I don't know why. It's probably because it's kind of messy to see. Anyway, and so now we are going to go into the pulmonary capillaries, right? But the pulmonary capillaries are weird looking because the lungs are different, right? So with the lungs, what you are going to have is this ultimately came from a pulmonary artery. It's delivering low oxygen blood to the lungs. But what's going to happen is these little tiny capillary beds are going to run by each little air bubble. And those little air bubbles are microscopic, and they're called alveoli. So what's going to happen, because we live on this planet, the air we breathe in is relatively high oxygen content and relatively low carbon dioxide content, right? The blood we are delivering is relatively high carbon dioxide content and low oxygen content because we already used it, right? Those are both lipid soluble, and so what happens is as this capillary goes by the air sac, the oxygen moves in down its concentration gradient, the carbon dioxide moves out down its concentration gradient, right? And then we deliver that blood back to a pulmonary vein. Does that make sense? There are so many alveoli in your lungs. There's so much surface area that in a healthy person, the surface area for gas exchange in your lungs is about the size of a tennis court. It's huge amount of surface area in your lungs. So they're really dense in a healthy person. So the blood goes back, right? Goes back ultimately into, even though you can't see them, generally 3 right lobar veins, 2 left lobar veins, and then ultimately it goes back into where? What vessels next? 2 pulmonary veins on each side, and then back into which chamber? Left atrium, exactly. And that's just pulmonary circulation. It's really freaking easy. There's not that many vessels associated with it. Everybody good with it? Okay, so systemic circulation, the way that I'm going to talk about it with you guys is to try to teach you flow at the same time as we learn the names of the vessels, because then it makes traces super easy, right? So first off, when we talk about systemic arteries, let's acknowledge that systemic arteries are all going to ultimately come from which chamber of the heart? Left ventricle. And they are all going to come from the same artery. And what artery is that? Aorta, exactly. So all of systemic circulation is ultimately from the aorta. And we will see, for those of you who have done more than a couple of your traces, they get super duper easy after you've done a couple of them. They're like really repetitive because it all starts and ends the same way, right? It's just a little bit of difference in the middle. Now, systemic arteries are relatively higher pressure, yes, 120/80 on average when at rest. The left ventricle has about 5 times the metabolic rate of the right ventricle. That's part of the reason that having a blockage in the LAD, or the anterior interventricular artery, it's called the widowmaker, right? You kill off that thing, you cut off blood supply to something that requires 5 times the metabolic rate, you're kind of hosed. Okay, now, the way to think about arteries, to understand what they're doing, and not just to name this as the brachial artery, is to think about what the artery is supplying. Because arteries are, of course, bringing blood to capillary beds. They're bringing oxygen and nutrients to capillary beds. So think about as arteries as supplying and veins as draining, yes? And then it makes you think about flow instead of just naming vessels. So that's the way we're going to talk about them today. Okay, so you already told me that systemic arteries flow from the left ventricle to the capillary beds, and every single systemic artery branches from the aorta, right? Okay, and we'll do that in order. We'll do ascending and then arch and then descending aorta. And then when you do systemic circulation in veins, first off, anatomy students hate the truth about veins, and that is that veins are very variable in their patterns and their numbers and their locations. And it's annoying. I totally agree that it's annoying. But it's not also particularly important because the fact that this cadaver here, the one that's closest to the stock room, has a left arm veins that are like nothing I've ever seen. I'm like looking at it going, what the hell is that bowl of spaghetti? But it doesn't really matter because all of them are ultimately going to end up in the basilic or the cephalic if you were looking at superficial circulation. And ultimately it's all going to go back to the same place. So what I'm telling you is expect variation and then realize that no one is really going to try to throw you because of the variation, right? So, and then there are ways to make sure that you understand what's going on. So you don't just label a vein at one point, you follow it to where it's going. If it's superficial and running all the way up the medial side, you're gonna call it the basilic, even if it looks freaking weird, right? If it's superficial and running up the lateral side, you're gonna call it the cephalic, even if it looks weird. Because the rule for veins is variation, it really is. And so really all you're studying is kind of what most people look like. So we think about veins, 3 times as many, and again, we talked about this last time. Part of the reason that veins and arteries are not exactly parallel is that a lot of times with deep arteries, you have a vein running with it, but then you also have superficial veins and you don't have any superficial arteries for obvious reasons, right? Not a really good place to put something high pressure that would kill you if it got poked, okay? So usually veins run along with arteries, especially in the limbs, plus the superficial ones, right? And when we look at systemic veins, don't think about a vein as going this direction. It always has to be going back to your heart. So like I said before, you won't have this test yet, but on your fourth test, I am just as likely to ask you which direction blood is flowing through a vein as I am to ask you to name the name of the vein, right? Or the gas content of the vein, because it's really the big picture that I want you to put together. So, but every systemic vein is going to end up in, ultimately, the blood's going to end up in what chamber? Right atrium. And it's going to end up getting there by 3 possible vessels. If it's coming from head and arms, it's going to end up in the superior vena cava. It's coming from below the heart, it's going to end up in the inferior vena cava. If it's coming from the heart muscle itself, it's the coronary sinus. So every single systemic trace will start in the left ventricle, right? Leave out through the aorta. Every single systemic trace will come back through the superior inferior vena cava or the coronary sinus to the right atrium, right? Okay, all right, so now what we are going to do is just acknowledge that we've already started this, because we already did the only blood trace that you guys would possibly have to do from the ascending aorta goes to what organ? Ascending aorta supplies what? What organ? The only 2 branches that you learned off of the ascending aorta we learned in the last set of notes. And you probably will have to do this on your test. So it would be good for you to know this. Yeah, the heart, exactly. So we already did this one, yes, didn't we? Okay. So if we're doing, here's how we're going to do systemic regional blood flow. We're going to deliver whatever comes off of the ascending aorta and then deliver it back. Then we're going to deliver whatever comes off of the arch and then deliver it back. And then descending thoracic and then deliver it back. And then descending abdominal and then deliver it back. Does that make sense? Okay, but we already did this one, right? So we already did the first blood trace, systemic blood trace. And it was this one, yes? So the only 2 branches that you learned from the ascending aorta were what? What are the 2 branches? Right and left coronary arteries. Let's just talk through it. You don't have to list it right now. You can do it later, but I would be prepared for a heart blood trace by Wednesday. Okay? Okay. So the left coronary artery gives rise to the circumflex, which runs around the back, right? And the LAD or anterior interventricular artery, which runs down the front. The right coronary artery gives rise to the marginal and the posterior interventricular artery, right? Good. And then the blood comes back through great, around the back, middle, and small cardiac veins, coronary arteries, cardiac veins, coronary arteries, cardiac veins. Yes? Okay. And then those all 3 dump into what vessel? Coronary sinus, which dumps into which chamber? Right atrium. Cool? Okay. So we already did that one. We already did the first systemic trace. We did it in the last set of notes because it was part of supplying the heart. So now what we can do is we can go to the next portion. So as we leave the heart, we had the ascending aorta, and then we've got the aortic arch, right? Okay. And the aortic arch has 3 major branches in most of us. Every once in a while we run into a cadaver that has 4, and it's confusing as hell because you have to figure out where that 4th one goes. But in most of us, there are 3 major branches off of the aortic arch. But I want you to think about why it's different left and right side. It is different left and right side because in the vast majority of us, the aorta arches over to the left side, okay? Which means, think about this. If you are delivering blood to the left side of the head and the left arm, you can go directly off of the aorta, yeah? But if you're delivering blood to the right side, you need to jog back over there before you can give blood to the right side of the head and the right arm. Does that make sense to you? Okay, so this first branch is that jog over to the right side. It's the most right portion of the aortic arch. It jogs over to the right side. It gives blood supply to the arm and the head, so it's called the Brachiocephalic Artery. Brachiocephalic, arm, head, okay? Or the Brachiocephalic Trunk. You can use trunk if you want to, okay? Do you see that one? But over on the left side, we don't need that because we're already over there. We can give blood supply directly to the head and directly to the arm. So this is the left common carotid, which will go to the head on the left side. and the left subclavian, which will go to the left arm. Is that good? Okay. So if you have a trace that goes to the right side of the head or the right arm, you're going to have one extra artery. Yeah? Every single time. Okay? The brachiocephalic artery or the brachiocephalic trunk. Good? And do you have two brachiocephalic arteries? No. You have two brachiocephalic veins, we'll see in a minute, but only one brachiocephalic artery. Good? Okay? All right. So, but FYI, after you get in to the subclavians and the common carotids, the blood flow pattern left and right is exactly the same, right? It doesn't change after that, okay? So after you're in the common carotids or the subclavians, everything's cool. Okay, so what we are going to do is off of the aortic arch, we are going to give blood supply to the head and the arm, correct? Aortic arch, blood supply to the head and the arm. Okay, so let's do what you do first, blood supply to the head. That's first dibs. Heart got first dibs, head gets second dibs, right? Arms get third. Good? So flip it around this way and we can actually see what's coming. So you can see it a little closer up here. You're going to go brachiocephalic, right common carotid, right subclavian, or left common carotid, left subclavian directly off the aortic arch. So we're going to flip around on this side and we're going to look at arterial supply, but this is the right side of the head. So that is the brachiocephalic artery. Okay, your textbook is totally inconsistent about whether they use artery or trunk. I prefer artery because it makes me remember that it's an artery. You can call it trunk if you want, but I usually use artery. Okay, so here's the brachiocephalic artery. So now what we are going to do is we are going to give blood supply to the head and then blood supply to the arm. So blood supply to the head is going to come primarily, but not exclusively, through the common carotid artery. Common, again, means it's going to split. This one is going to split to deliver blood to the outside of the head, the skull, the facial muscles, right? And then the inside of the head, the brain, okay? So this one is called the external carotid artery, yeah? Mm-hmm. And this one is called the internal carotid artery, and it goes through a hole that you learned. What is it? Carotid canal. Yes, it goes through the carotid canal. Okay, so this one is going to go up through the carotid canal and give. The pair of internal carotid arteries delivers 75% of the blood supply to the brain. They are super duper important, okay? Which is why that pass out game that kids play, do not play that damn game. Find other ways to get your jollies. Don't do that, okay? Don't do it. Kids still do that. And I think it's because they don't drink here, and they're like, how else can I get high? I'm like, well, really, it would be better to have a beer, honestly, than to try to cut off blood supply to your brain. What? The pass-out game? They basically compress their neck until they see stars and practically pass out because they're bored. They can't have sex or drink. Okay, now let's look at what that actually does. Right? So if you look at an inferior view of the brain right here, you will see that those two internal carotid arteries come right up by the pituitary gland and the optic chiasm, right? And they deliver collectively 75% of the blood supply to the brain. We'll get the other 25% in just a second. Please note the redundancy in circulation you see in the brain right there. It's going to be really important in a second. Okay, but what about the rest of the blood supply to the brain? The rest of the blood supply to the brain comes, if you follow, right? However you get into the subclavian, it's a branch off of the subclavian. So here I'm on the right side, so I went brachiocephalic subclavian. Then look at this branch right here. This branch right here is going through the transverse foramina of the cervical vertebra, and they're paired, and they are called the vertebral arteries. Here's what they do. They run up the transverse foramina, and then they go anterior to the medulla oblongata and run up the foramen magnum, right? And then they're going to come together. So watch what they look like. Okay, so these are the vertebral arteries. Here are the vertebral arteries, these two, right? They're going to come anterior to the medulla oblongata, and they're going to join together and run down the cleavage of the pons. Remember how the pons was like that? That's the basilar artery, and they're going to form the rest of the circle. This is a super duper important example of collateral circulation, because I want you to think about what would happen, for instance, if I blocked this portion. Well, you get blood around that way, right? What would happen if I blocked this portion? Well, I get blood up here and back from here, right? Okay, so this collateral circulation and the fact that it leads to a circle of arteries that deliver most of the blood supply to the brain is called the cerebral arterial circle, or the circle of Willis. Okay, super duper important. I know how important it is because I busted one of these 4 arteries and still lived through it. I busted this one right here, which is my right vertebral artery. And it's super interesting because I totally lived through it, although I wonder if I used to be smarter. I have no way of telling because this is as smart as I am right now and I can't remember. Okay, so show you, can you identify the arteries on this? Okay, so brachiocephalic, right? Right common carotid, left common carotid, going to the internal carotids that you can see going through, right? What are these 2 back here?
Vertebral.
Those are the vertebrals. Okay, so what happened, I really can't believe I lived through this, but I didn't even, it was 6 months before I went to the doctor. So what happened was I was super duper stressed out, and I've got cardiovascular weirdness anyway, and I was sitting on the couch, and all of a sudden I could hear my blood pulsing against my skull, like being amplified by my skull, super loud, so that if you were sitting right here, I couldn't hear you. So it was like, really loud. But I was too damn stressed out to go to the cardiologist. I was like almost getting a divorce. We didn't get a divorce. We almost got a divorce. Everything was shit. So, you know, I mean, have you had that point in your life? Just everything's shit and I don't have time to deal with more shit, so I'm not going to deal with it. So I didn't go to the doctor. Good choice, Melanie. But I didn't die either. So when I finally got it together and went back to the doctor, I went to the cardiologist and he was like checking heart stuff. And I was like, yeah, but while you're there, would you mind taking your stethoscope and just listening to this part of my skull? And he's like, what? I was like, just would you? Huh? And then he did. And literally he said, oh shit. Oh shit. And then he sent me to the specialist at the U and I found out some really cool shit. And the really cool shit is that what happened was that my right vertebral artery had a weakness in the wall, and when I got super duper stressed out, I busted a hole in the damn thing, and it was bypassing circulation to my brain altogether. I don't know why the hell I didn't have a stroke, and it was dumping directly from my right vertebral artery into my right vertebral vein and not going to the capillary bed. So it busted a hole between those. And so I asked a stupid question. Remember, I was stressed out. And he was like, okay, we have to fix this. And I was like, do we really? Because it sounds like hard. And he's like, Melanie, what is going to happen with the pressure if I let that thing continue to dump into your right vertebral vein? Because can veins handle arterial pressure without going through a capillary bed to dissipate the pressure? They can't. And so if I had let that go on, it would have ballooned out my vertebral vein, and I would have had an aneurysm and probably bled out. So we had a choice to make. And he let me talk through the choice. He didn't let me make it. He let me think I was making it, but I didn't make it. He said, okay, we can do 2 things, just theoretically. We could stitch it up, right, and send the blood back to your brain. But in the stitching process, we might actually form a clot, and that would get thrown to your brain. So no. So what they decided to do was, because I didn't die, they figured I was okay without it. So he stuck up my femoral artery. So they did this whole dye thing, and I got to watch it with diagnosis. It's super cool because you could see the blood just go straight here, and then it would just dump straight in. It wasn't actually going up that road, but it was still getting blood flow. It just took a while to get there. It was interesting. So what he decided to do was shut it down so that it wasn't dumping into the vertebral vein, which makes perfect sense now that I'm not stupid and asking stupid questions. So he went up my femoral artery all the way up into this vessel back here, and I got to stay awake for the whole thing until he got into my neck because I wanted to. And then he's like, I'm putting you to sleep. And then he videotaped the rest of it for me, which was awesome. And I got to watch it afterward. I still have the videotape. And then what he did was he shoved $30,000 worth of platinum coils into that vessel in my brain until it shut down. Just like completely shut it down. Like, so they had the dye going the whole time until he saw no dye going into the other side. And then once it was shut down, I was good. And then all I had was a little scar right there, right? And I didn't die. So great example of collateral circulation, totally works. And he's not even worried about me anymore. He's like, you can come every 3-4 years, Be fine. So anyways, collateral circulation and the cerebral arterial circle apparently works very well. Okay, so now venous drainage of the head. So all of the blood that's coming back from the head is going to ultimately end up in what vessel? Blood coming back from the head is going to end up in what? Superior vena cava. But how do you form a superior vena cava? You form a superior vena cava by the junction of two brachiocephalic veins from both sides of the head and the arm. So remember that you are going to end up back in the brachiocephalic vein. When you put the two of them together, they form the superior vena cava. Note to self, that means that although you have one brachiocephalic artery, you have two brachiocephalic veins. Yes? Okay, two brachiocephalic veins. So let's get the blood back into the brachiocephalic vein. So the blood from the outside of the head, right, is going to dump into the external jugular vein, which usually dumps into the subclavian and then gets gathered into the brachiocephalic. Is that okay? Okay. The blood from the inside will all end up in the internal jugular vein that goes through another hole that you learned, jugular foramen, right? And that is going to get dumped into the subclavian. When you get all the blood from the head and the arm together, then it's brachiocephalic. Does that make sense? Because it's got brachio and cephalic, okay? So right here it will be brachiocephalic. And then last little bit of blood that we have, that 25%, would get dumped into the vertebral vein, that gets dumped into the subclavian, that gets gathered into the brachiocephalic, and into the superior vena cava. Does that make sense? Okay. So are these hard? If you just look at where they're going? No, it's not actually hard. So it's brachiocephalic after you've gathered everything up. This one's coming from inside the head. What do you want to call it? Internal jugular. This one's coming from outside the head. What do you want to call it? External jugular. This one's going through the transverse foramina. What do you want to call it? Vertebral. And this one is running under the clavicle. And so that's the subclavian. Does that make sense? So it's pretty good. It's pretty easy and logical once you get into it. Okay, but let's go ahead and acknowledge that draining blood from the head connects to a story that we've already learned. And that story that we've already learned is this, which is all of the blood from those dural venous sinuses is draining from the brain, but it's also draining what other fluid? Cerebrospinal fluid. That's why they're big and sinusy, right? All of these are collectively going to dump into the internal jugular vein. I won't make you do the order of drainage in the sinuses, but all of the sinuses collect ultimately into the sigmoid sinus and then into the internal jugular vein, which is how you get blood out of the head. Good? Everybody good? Okay. So, everybody all right with that? Okay. Is it just me, or are blood traces relatively simple, right? They're not that bad, huh? You don't like them? I think they're fun too. I like them. I think they're relatively easy. The only one that I hate is the thoracic cavity. I don't like those veins. Little bastards have too many names. Okay, so now we're going to do arterial supply to the next place that gets it. So heart was first, right? And then head is next, and then arms, right? So now we are going to do arterial supply to the upper limbs. So let's talk about that. So the arterial supply to the upper limbs, whether you're starting right or left side, get to the subclavian artery, right? Get to the subclavian artery, and then you are going to head to the upper limbs. Again, just to be annoyingly repetitive, which side has an extra artery on the way there? Right side. What is it? Brachiocephalic artery, okay? The left side goes directly off of the aortic arch, the subclavian, the left subclavian, okay? But we're on the right side here, so the brachiocephalic was right there, and then we go into the subclavian. So it's pretty damn easy, guys. It really is. You learned the names for things. You've done harder stuff than this. So as it goes under the clavicle, what do we call it? Subclavian. As it goes through the armpit, we call it the axillary. As we go through the arm, brachial. And then we're going to split and go lateral, and that one's going to be the what? Radial. Medial. This one's going to be the ulnar, okay? And you don't do these in lab, but they're not hard. The arches, just FYI, the blood, of course, does go to your fingers, right? It's hard to dissect these out, so we don't usually make you do them on the cadavers. But the way it works is it forms an arch here and then an arch there. They're not very superficial because they're arteries, but one of them's more anterior and one of them's more posterior. They are called the deep palmar arch, that's on the back side, and the superficial palmar arch is on the front side. It's not that superficial. And then they give rise to the digital arteries, and the digital arteries supply your fingers. So if you ever do a finger prick, right, to test your blood glucose or whatever the hell you're testing for, it is supplied by one of those digital arteries. Good? So that's pretty easy, isn't it? Okay. And then we do blood flow back through the venous system. The only reason that this is hard at all is because A, you got superficial and deep, and B, for me, maybe it's just my limitations as a human, I have a hard time with spatial orientation on these 2D pictures. I have a hard time figuring out what's behind and in front, especially when you're down here, like, what the hell am I looking at down here? But luckily, I probably will not ask you to identify superficial versus deep on a 2D picture, but I might have you do a trace through it, right? So now we're going to get the blood back from where we got it. So what do you think? Even though they're labeled, what do you think these are not labeled? What do you think these veins are called? Yeah, those are the digital veins, and those give rise to a superficial and a deep venous arch. The superficial one is superficial. It's on the back of your hands. If you do this, I can actually see mine as an arch, right? If you hold your hands down for a couple minutes, like 30 seconds, right? Then you'll be able to see them really, really well, okay? So, and of course, that's a really common place for IVs, right? It's really easy to get at. Mine stick out quite a bit. You can see them going all the way down there. So the deep ones are more anterior and the superficial ones are on the back side, right? So if we're doing a superficial trace to get it back, start digital, go superficial that's on the back side, and then that will lead up to the basilic and the cephalic, right? Okay, basilic, boob side, that's how I always remember. Cephalic on the other side, BC, okay? So basilic, cephalic, they do any damn thing they want between them, really, honestly, anything. But the most common thing is that they'll have a couple of different anastomoses. There's usually one right here, which is, of course, a really common place for blood draw, which is called the median cubital veins. If there is one, it's called the median cubital, but really commonly, and also on your Wireman models, there are two, okay? And if it's okay if there are two, because they're pretty easy too. Then you have a V instead of a slash, and this is the median basilic and the median cephalic, right? That doesn't really matter. It's not particularly important what pattern they have. And then that first cadaver next to the storeroom, I don't know what the hell's going on with his arm. Like, it was a bowl of spaghetti. I was like, I don't even know what I'm looking at here, but I'm like, okay, that's the basilic and that's the cephalic, and there's some shit between them. You know, let's just give them a name. I'm going to call that one George. I don't know what the hell they were. So it doesn't matter, and I don't try to trick you about this, but there's always at least one anastomosis between them, and it's usually elbow level, and sometimes there's two. So basilic and cephalic, and then you follow these up, and where do they dump? Wherever the hell they want, really, okay? But most commonly, the basilic dumps into the brachial. Sometimes it dumps into the axillary if it wants to. It doesn't matter. Cephalic usually dumps a little further up. Sometimes it can dump all the way into the subclavian if it wants to, okay? Ultimately, where they gather up is that they are all going to gather into the subclavian vein, right? Okay, regardless of where they dump. And I don't try to trick you with stuff like that, because that would be silly. Because if I write a question that has 25 right answers, it takes me 7 years to grade it, and that would be dumb, right? I respect my own time and yours a little more than that. So basilic and cephalic ultimately end up in the subclavian vein. Okay, so that's the superficial drainage, right? And then the deep drainage is easier. The deep drainage, again, digitals, follow those up. This time the palmar arch is going to be more anterior. It's called the superficial palmar arch, palmar venous arch. And then if you follow those up, they will go into two ulnar veins, usually two radial veins that run with the radial and ulnar arteries. Sometimes it's 1 and 2, sometimes it's 1 and 1, does whatever it wants. Either way, as they start moving up, the radial and the ulnar, and they go past the elbow, they will be the brachial. Usually there's 2 brachial, sometimes all the way up, sometimes just for a minute, okay? Regardless, if you're in the arm, it's going to be the brachial veins, okay? And the brachial veins are going to go up and do whatever the hell they want. Eventually, they will actually become the subclavian vein. Yeah? Okay, so brachial to subclavian. Is that okay? And then from the subclavian, get me back to the heart. Subclavian.
Subclavian, inferior vena cava.
Subclavian, you forgot one.
Brachiocephalic.
Brachiocephalic, superior vena cava, right? And again, it becomes brachiocephalic after you've gathered up all of the arm stuff and all of the head stuff, hence brachiocephalic. Does that make sense? Okay, go ahead. It's because it's headed toward the brain. Somebody just named it, oh, it's going that direction, right? It's not a particularly good name. Okay, but that's a good question. All right, everybody good with venous drainage of the upper limb? Everybody good? Okay, and then now we are going to go blood supply to the next place, and the next place is, okay, so we just did heart, that was first, head is second, arms is third, and then we do thoracic arterial flow. But is there really that much left in the thoracic cavity that hasn't gotten blood flow already? There isn't, right? Because the lungs get primarily pulmonary flow, and the heart you took care of first, yes? So you just got a few things left. Like, for instance, you need to give blood supply to the intercostal muscles, right? And the skin around the intercostal muscles and all that kind of stuff. And then a couple more places that aren't shown on here, like the esophagus runs through there. It probably needs blood. Its blood, not surprisingly, even though it's not in the picture, comes off of the descending thoracic aorta. Good. And then counterintuitively, before we do this part, there are parts of the lungs that don't do gas exchange with the air, like the bronchioles, right, and the external portions of the lungs. Those, although it sounds counterintuitive, get systemic arterial blood from an artery called the bronchial artery. Does that make sense to you? Right? If they're not doing gas exchange with the air, then they need systemic blood. So there is an asterisk when people say that the lungs get low oxygen blood. Most of them do, right? The gas exchange portions do get low oxygen blood. Okay, but let's look at these. So basically, all this is really showing you is that you are going to get blood supply to the intercostal arteries from the descending thoracic aorta. There are actually 3 intercostal arteries, but again, I can't really tell spatially what these are, but I will tell you that there's the anterior intercostal artery, the posterior intercostal artery, and then there is the internal that run on the inside, okay? But for me, you don't have to be able to tell the difference between them on an image. It's too hard. I mean, it's hard enough when it's color. It's really hard when it's black and white. Okay, so those are, that's just the descending thoracic aorta that gives rise to those. And I put the esophageals and bronchioles on there. There's no pictures of them, but conceptually know that the esophagus is supplied from there. Okay, and then what everybody hates, myself included, is the venous drainage of the thoracic cavity, because they're hard to see. It's like weird looking, but I will tell you why it's weird looking, at least so it'll make it slightly easier to understand. So what we are going to do with thoracic cavity venous drainage is we have to get it all into the superior vena cava, but because the aorta is more left, the vena cavae are more right. So if you are draining the right side, you can go more directly into them. If you're draining the left side, you have to make a couple of jogs to get over there. So although it doesn't make it any more pleasant, at least you know a reason why you've got extra vessels on the left side. So let's look. On the left side, if you are dealing with the intercostal muscles from the upper ribs, they usually have this drainage pattern. Intercostal veins, you with me? Okay, this little booger right here, which is called the accessory hemiazygous vein, which dumps into the azygous vein, which dumps into the superior vena cava. Okay. If you are draining the lower left ribs, then it goes intercostal veins, hemiazygous, that one goes behind and dumps into the azygous, which dumps into the superior vena cava. If this were me, I would draw lines. I would draw arrows to show me which direction the blood is going. Okay. Why is all of this named this? Azygous, as in not a zygote, means unpaired, because all of these vessels are unpaired, right? There's no pairs. Okay, all right, but if you are draining the right side, you can do it more directly. you can go directly from an intercostal vein into the azygos into the superior vena cava. So it's a shorter story. Good? Not do you like it, because nobody likes it. You can see it on the Wireman model, though. I don't think it's dissected out really well on any of the cadavers because they're really hard to dissect out. Okay, everybody good? Okay, you guys are really quiet today. Why is that?
Great information.
Yeah, oh, that's it. You're just spellbound. Okay, now we will do arterial flow through the abdomen, and then we'll do hepatic portal circulation, and then I'll let you guys go for today because you're ahead of the other class. So now we are moving down. So we did ascending aorta, we did aortic arch, we did descending thoracic aorta. Now we're going to go through the diaphragm, right? And so we are going to do descending abdominal aorta. So as we do descending abdominal aorta, let's just get the easy stuff out of the way first, okay? So the descending abdominal aorta gives rise to arterial circulation in the abdominopelvic cavity, and then the legs and the genitalia. Yeah? Okay. But abdominopelvic comes first, right? Okay. So let's look at the easy things that come off of the descending abdominal aorta. If you can't figure out what that vessel is called, I don't even know what the hell to tell you. What is that? That is the renal artery, yeah? And they go directly to the kidneys, so they are like, if somebody asks you that on a practical, they are being so cool to you. And you should be able to tell a renal artery from a renal vein very easily. Just touch them. You'll be able to tell the difference. So those are the renal arteries, left and right. And then we have the suprarenal arteries that go to the adrenal or suprarenal glands. Don't let this one confuse you. Sometimes it pokes through the diaphragm and then comes back in. It's still the suprarenal artery. Can do whatever the hell it wants. Okay, we'll get the big ones in just a second. The other things that are going to be important are these two. And they're going to the gonads, so what do you want to call them? Gonadals, unless you know the sex, and then you can't call them gonadals. Then in a woman, you call them ovarian arteries, and in a male, you call them testicular arteries. Now, of course, because the testicles descend through the inguinal canal, the testicular arteries are going to be longer, yeah? They lengthen as the testes move through the inguinal canal. So those are the right and left gonadals, unless you know the sex, and then they're not gonadals. Okay, and then we have these three branches. So let's get the big picture of these three branches before we get into the trees. Let's look at the forest. This big honkin' branch right here is called the celiac trunk. It's the one that's just inferior to the diaphragm. And it supplies 4 different organs. Can you think about what it supplies? Spleen, yes. Stomach, liver, first portion, a little bit of the pancreas, actually, I wasn't thinking about that, but a little portion of the small intestine called the duodenum. Yeah? Good? Okay. And then we run down to the superior vena cava. And the superior vena cava supplies the entire rest of the small intestine. Oh, sorry, I said superior vena cava. Superior mesenteric artery. I was testing you. You did great. Superior mesenteric artery. Superior mesenteric artery supplies the entire rest of the small intestine and the proximal portions of the large intestine. Good? Mm-hmm. The inferior mesenteric artery supplies the distal portions of the large intestine. But let's add a little bit more detail to that. So the one that people have the most trouble with is the celiac trunk. And that's understandable, but it's not that bad when you actually look at it. So let's look at the celiac trunk. Okay. So the celiac trunk is going to be, again, just inferior to the diaphragm. I want you to think about what it's supplying. So the celiac trunk is going to have 3 big branches and then some branches off of those. It's going to have this one that runs behind the stomach, almost always has this little wiggle in it, I don't even know why, and goes to this organ. What do you want to call it? Splenic artery, yes. Do not identify it here. Follow it to where it goes and you will confirm, right? It's not as hard if you follow them all the way to where they're supposed to supply. Go ahead.
So on different models that I looked at, sometimes after that celiac branch, sometimes it first branches to the left gastric and sometimes first to the spleen. Do they vary?
It varies a lot. Yes, it varies a lot. Sometimes they actually are together until they get down here and then they branch. So again, what you want to do is follow them to where they go so that you know that you're calling the artery the right thing. Because regardless of how it got there, if it supplies the spleen, it's the splenic artery, right? Does that make sense? Okay. And then this little guy right here which dives around the lesser curvature of the stomach from the left side. What do you want to call it? That's what I want to call it too. I want to call it the what gastric? Yeah, that's the left gastric artery because it supplies the stomach from the left side. Does that make sense? Okay. It'll form an anastomosis with its buddy over here, and we'll get that in just a second. So we just did splenic. We did left gastric artery, right? This other big branch right here is where people get confused. This is called the common hepatic artery, but it doesn't just supply the liver. Okay, it supplies the liver plus, okay? So the common hepatic is going to branch. Follow the branches to figure out what the name is, okay? This guy is going around and it's going to supply the greater curvature of the stomach and the first portion of the small intestine, which is called the duodenum. So what do we call it? We call it the gastroduodenal artery. Does that make sense? Okay, it also supplies the pancreas, yes. There's a branch off of it. And then this guy right here, do you see? Is going to branch off and it's going to supply the lesser curvature of the stomach from the right side. It's going to form an anastomosis with its buddy. What do you want to call this one? Right gastric artery, right? Right gastric artery. And then this little guy right here will actually continue to the liver. And so now you are proper hepatic artery or hepatic artery proper. Get all three of those words in any order because nobody is consistent about it and you're totally cool. Okay, and then that one will branch to the right and left hepatic arteries. Everybody okay with that? Okay, so the right and left hepatic arteries. Good? Okay, so if you follow them, whether it's a model or a cadaver, it ends up showing you the answer if you just follow it to where it goes. Okay, all right, so now we're going to go down and do the next branches. And the next branches, I don't know why they didn't do this, but this branch right here, so the celiac trunk is cut off. They took out all of the organs that we already supplied. Plus they took out the entire small intestine because it's big and in the way. But what the superior mesenteric artery supplies, it has all of these little arteries that are coming off of it. You don't have to know them. But they run through the mesentery, yeah? They're called the intestinal arteries. And they are going to supply the entire rest of the small intestine. You with me? Okay. We did the duodenum. They're going to take care of the entire rest of it. And look, they are also going to supply the proximal portions of the large intestine, which are the ascending and transverse colon. Do you see that? Okay. And then its buddy, the inferior mesenteric artery, is going to supply what's left. It's going to run through the mesentery, but the inferior portion, and it's going to supply what's left, which is the descending and sigmoid colon. Everybody okay with that? So it just took care of pretty much arterial flow to the entire abdominal cavity, not necessarily the pelvic cavity, but the entire abdominal cavity. Everybody okay with that? Okay. Some of you guys look confused. You all right? Okay. All right. So we did suprarenal, renal, gonadal, and we got superior and inferior mesenteric. And then we do the venous drainage of the abdomen, and I'll let you guys go after this, but I do want to talk about venous drainage of the abdomen because it's weird. So first off, let's get the easy part done. So the easy part done of the venous drainage of the abdomen are the ones that kind of do what you expect them to. Okay, so the renal arteries were supplied directly from the abdominal aorta, and the renal veins drained directly into the inferior vena cava. Everything here is ultimately going to end up in the inferior vena cava, but sometimes it's a pretty circuitous route to get there. Okay, and then the suprarenal veins drain wherever the hell they want. They either drain into the renals or into the inferior vena cava, and it's not particularly important, the pattern that they do. Okay, the gonadals, generally, this is the general truth, is that the right gonadal, testicular, ovarian, whatever you want to call it, dumps into the inferior vena cava directly. But for whatever the hell reason, and nobody really knows why, the left gonadal usually dumps into the left renal. Okay? And it's not that important. Again, I don't ask questions like these about veins when the venous exception to the rule is not functionally important, then I don't usually stress it. But when we run into situations like the hepatic portal system, then it's functionally important, right? Then that's when I want you to actually know the flow pattern. Okay, so that's all of the easy ones. And then notice, of course, before we go any further, that what you do not see on this picture is you don't see the parallels to the arteries. You do not see dumping into the inferior vena cava a celiac vein, an inferior mesenteric vein dumping into the inferior vena cava, or a superior mesenteric vein dumping into the inferior vena cava. You don't see anything until you run up here and see the hepatic veins. And that is because of the hepatic portal system. And the hepatic portal system is functionally important. It's also one of my favorites, but it's not until your fourth test, so you've got some time for it. Okay, so what is the hepatic portal system and what is the function of the hepatic portal system? The function of the hepatic portal system is that all of the food that you eat is not sterile. It's not necessarily void of toxins or pathogens. And so before you send it back into systemic circulation, you need to run it through surveillance. Yeah? And the surveillance happens in the liver. So what we are going to do, I don't know why they didn't show you this picture, but the inferior vena cava would be running right back behind here, right? But we're not going to dump into it. What we are going to do is we are going to dump all the way, all of that blood into the liver first, let it percolate slowly from the bottom to the top of the liver, give ourselves a chance for those macrophages to gobble up whatever's funky in it, and only after we do that will we send it back into the inferior vena cava. Does that make sense? Okay, so these vessels, and there are more than the ones that you learn, but these vessels collectively are called hepatic portal circulation. So let's just look at the big picture that we can see here. And you guys have done this in lab. Hasn't almost all of you done it in lab? Yeah? Okay. There's like one more class today, I think, that's doing it in lab. Okay. So what we are going to see is this one. You don't have to memorize it if you look at where it's coming from. It is coming from the descending and sigmoid colon, right? So what artery supplied the descending and sigmoid colon? Inferior mesenteric artery. This is the inferior mesenteric vein, right? That's draining the same thing that the inferior mesenteric artery supplied, okay? And then this one right here is supplying the proximal portions of the colon, and although it's cut off here, I will tell you that it's also supplying almost the entire small intestine. So what are we going to call this one? Superior mesenteric vein. Good. And then this one is coming directly from the spleen. What do you want to call that one? Splenic vein. So what we are going to see is, do you see the chair? Do you see that it's a chair? I'll draw the chair for you. Do you see the chair? Okay. Right. So what was this one? Inferior mesenteric vein. What was this one? Superior mesenteric vein. Which direction is blood going through those? Up. Yes. What is this one? Splenic vein. I'll tell you why the spleen is involved in the story in just a second. Gather those all together. This blood is going through a great big wide vessel. It's huge, okay? And that is called the what? Hepatic portal vein. A portal vein breaks the rules of circulation in this way. Circulation generally goes heart, arteries, arterioles, capillaries, venules, veins, heart, right? But a portal vein goes heart, arteries, arterioles, capillaries, portal vein, another set of capillaries, venules, veins, heart. So what it does is it puts two groups of capillaries in series, because everything that came from these capillaries needs to go to these capillaries before it goes back into circulation. That's what a portal vein does. So what the hepatic portal vein is going to do is going to do something that veins don't usually do. It's going to supply the capillaries of the liver. Yes? Okay. It's going to deliver blood not to the heart, but to a capillary bed. So it's breaking the rules that you usually have. So this is the liver. So it's basically like a chair with a big old pillow on the top. Okay. It's going to slowly percolate through the liver, and then ultimately it's going to deliver blood back through the hepatic veins into what vessel? IVC. Yeah? Okay, but there's more to this story, just a teeny bit more to the story. And the teeny bit more to the story is that now we have to acknowledge two true things about the liver. The liver gets two different kinds of blood. So we just a minute ago talked about the fact that the liver receives blood from the hepatic artery proper, But now I'm telling you that it also receives venous blood. So this isn't part of the hepatic portal circulation, but it's part of the story. So hepatic artery proper delivers oxygenated blood. The hepatic portal vein delivers deoxygenated blood. And what happens is that blood actually gets mixed in those big sinusoid capillaries. And so it percolates really slowly through. And what occurs as it goes really slowly through is that the liver takes its fair share of oxygen from the oxygenated blood. But then it is also taking pathogens and toxins from the deoxygenated blood. And so by the time the blood gets to the top side and gets delivered into the hepatic vein, it's going to be different than either this blood or this blood. Does that make sense? So I will talk to you guys about this after the test again, but what ultimately you will have to do for your fourth exam is to compare oxygen content, toxin, pathogen content, and compare it in the hepatic portal vein and in the hepatic artery proper and in the hepatic vein. Just to sort of make you put together what's going on as you go through there. That make sense? So you can sort of figure out what's going on, okay? In addition, the nutrients don't change that much. The nutrients will be, just so you know, really high in these, okay? They actually don't change that much as they go through the liver. The liver takes a little bit for itself, then it sends most of it back into circulation. Everybody okay? Okay. So we'll pick up with hepatic portal circulation right after your test, and we'll stop there for today.